As a future engineer, or in tant que futur ingénieur, for those of you diving into your first year Common Core, you are going to literally design, calculate, and build the world of tomorrow. But before you draft a single sketch or program your very first simulation, there's a fundamental truth we need to establish. Every design, every experiment, and every calculation you ever make is going to rely on precise measurements. I mean, measurements are the high-stakes foundation of your entire profession. Make one tiny mistake here, and the whole thing collapses. So consider this explainer your essential survival syllabus for successfully navigating this foundational coursework. Let's get right into it.
So here is our game plan for today. 1. The engineer's language. 2. Base quantities. 3. Derived quantities. 4. Scalars versus vectors. And finally, 5. The importance of direction.
Starting off with Section 1, the engineer's language.
Just like musicians all over the world read the exact same sheet music, engineers use the International System of Units, or the SI. Established by the International Bureau of Weights and Measures, this is literally the universal grammar accepted globally across all scientific disciplines. And right at the heart of this language is the concept of a physical quantity. Let's read this core definition together because it's absolutely crucial. A physical quantity is any property of a body, material, or physical phenomenon that can be measured experimentally and expressed by a numerical value together with a unit. Now, this isn't just academic jargon. This concept is exactly what allows us to compare observations and reliably predict the behavior of insanely complex physical systems. Okay, let's dive into this. Every measurement breaks down into 2 strict steps. Step 1 is the numerical value. Step 2 is the unit. Because without a unit, a number means absolutely nothing in physics. Imagine I just walk up to you and say 10. Well, 10 what? It's totally meaningless. But if I say 10 kilograms, suddenly we have a precise mass. This is the unavoidable basic mechanic of literally any engineering measurement you will ever make.
All right, moving on to Section 2, base quantities. So if units are our language, these fundamental quantities are the alphabet. They are completely independent. You can't define them from any other physical quantities. And here is that alphabet, the 7 SI base quantities. We've got length in meters, mass in kilograms, time in seconds, electric current in amperes, thermodynamic temperature in kelvins, amount of substance in moles, and luminous intensity in candelas. Take a second to really soak this in. These 7 ultra-precise units form the foundation of all measurements in the known universe. This is your absolute bedrock. Which brings us to Section 3, derived quantities. Now, if the fundamental quantities we just looked at are our alphabet, derived quantities are our vocabulary. By taking those base blocks and simply multiplying or dividing them, we start building much more concrete and complex engineering concepts. For example, notice how combining a length divided by a time gives us velocity in meters per second. The really cool part is seeing how seamlessly it all chains together. You take mass, multiply it by acceleration, and boom, you create force, expressed in newtons. Vital tools like pressure in pascals or energy in joules are ultimately just clever combinations of our basic alphabet. That takes us to Section 4, scalars versus vectors. All right, this brings us to what I like to call the grammar of movement. It's a concept every single first-year student absolutely must master, because measuring is great, but knowing exactly where you're going is even better, right? On the left side here, we have scalar quantities. These are entirely specified by a magnitude alone. Things like 25 degrees Celsius, 15 kilograms. The addition is just classic algebra. You don't need a direction. But on the right, watch out for vectors. Displacement, force, acceleration. These absolutely require a magnitude and a direction. And because of that, the addition becomes vectorial. It's a whole different ballgame. Let's unpack that a bit more in Section 5, the importance of direction.
I really want to slow down and emphasize the immense real-world stakes of this distinction. In engineering, omitting a direction doesn't just give you a slightly off result, it entirely changes the physical effect of the quantity. And this brilliantly illustrates the point. Focus specifically on angle theta. That angle precisely defines the direction of the action. Sure, the length of the arrow represents the magnitude, but without that angle theta, you have absolutely no idea where your action is actually being applied. Visually, it's super simple, but it perfectly captures the essence of a correct vector representation.
So let's do a quick practical test, straight from our source material, to make sure we're actively applying this. Imagine a car travels 120 kilometers east. I want you to mentally classify these 4 terms for me: distance, displacement, speed, and velocity. Are they scalars or vectors? Take a second. Okay, let's reveal the solution. Distance is a scalar because it only has a magnitude, 120 kilometers. Displacement, however, is a vector because it specifically demands that direction, east. In the exact same way, basic speed is a scalar, but velocity, which translates a displacement in a given direction over a certain time, is a vector. If you nailed that, awesome. You just proved you've got this new physics literacy down.
Let's quickly look at a second example that reinforces this golden rule. Imagine a force with a magnitude of 150 newtons, acting at a 30-degree angle above the horizontal. The absolute crucial takeaway here is that magnitude alone does not define the force. Think about it. If you only change the direction, let's say you push at 90 degrees instead of 30, the entire physical effect on the object changes radically. And that is exactly why force is, and always will be, a vector quantity. To wrap up, I want to leave you with this provocative final thought. If you forget the direction of a force in your calculations, what are the actual consequences going to be for your very first engineering design out there in the real world? Always remember that these first-year concepts, whether it's respecting fundamental SI units or never ever forgetting the angle of a vector, they aren't just mathematical abstractions. This is the exact language you're going to use to guarantee the safety, stability, and innovation of tomorrow's world. Keep your eyes open, stay curious, and always apply the right language.